Okay, so let's look at this circuit here. So here it says the switch has been closed for a long time. It opens at t equals 0 seconds. Find an expression for v at t. So instead of stepping it through as like the previous example in the video, in the previous video did, we're just asked to find v at t, which we know we have to have some initial voltage, e to the minus t over tau. So when we have a circuit like this with a switch that's been closed for a long time, we usually just go and attack and find V0 first. So first thing to remember is, okay, that's closed, so that's just a wire there. But then a capacitor, when charged, acts as an open. So there's really an open circuit here right now. And this voltage here, if I think about it, this voltage right here, I'll label this voltage VA. Well, that's the voltage across that capacitor because, of course, the bottom I would just connect to ground. So that's the voltage across the capacitor. So VA is my initial voltage. And then, of course, if I have here, this is 600 volts. And then this here is an unknown voltage VB. Now, there are other ways you could go about analyzing this problem. You could do loop analysis, for instance. You could find the currents. You could also do some combinations of things in parallel and series and find the voltage that way. But I'm just going to go ahead and do a nodal analysis here just to make sure we kind of refresh all of our analysis techniques. So we have VA minus 600 over 100K plus VA minus VB over 20K, and this is equal to 0. So I'd multiply this by 100K, and if I do that, you'd get VA minus 600 plus 5 VA minus 5 VB, and my equation I'd wind up with would be 6 VA minus 5 VB equals 600. So I'll just put the other equation over here, because if we have this other one here, if we look at node VB, it's actually a pretty simple equation. I'd have VB minus VA over 20K plus VB over 60K plus VB over 60K, and this is equal to 0. And then if I, again, kind of clear this out, multiply through by 60K, this would be 3 VB minus 3 VA plus VB is equal to 0. And so we'd wind up with minus 3 VA plus 5 VB equals 0. And now it turns out that that works out pretty nicely for us, because I can just look at these two equations here, and I can simply just add those two equations together. And what I mean by that is if I write them as like this, then I add those two together, well, I wind up with just 3 VA is equal to 600. So VA is equal to 200 volts. And I don't really need VB. So VA is 200 volts, so my initial voltage is 200 volts. Now, I just want to remind you here that this switch is closed, so the capacitor is charged up completely. So it's got 200 volts across it. Now when you open it, it's still going to initially, for one precise moment in time, that capacitor is still going to have 200 volts across it, and then it's going to start discharging into the resistors. Okay, so we got 200 volts across it. So now we need to work on finding what tau is. So what is tau? Well, we know we need to look at the circuit with the switch being open. Which, if I look at the circuit with the switch being open, this is what I have here. I've got a 60K, another 60K, and a 30K. Oh, no, that wasn't 30, that was 20. 20K. And this was 0.4 microfarads. And now we know, or we should know from our previous lessons, that tau is simply just R times C. But we might say, okay, well, wait a minute here. R times C, what's the resistor I should use? And saying what resistor should I use is the wrong way to think about it, actually. What we want to think is not just what is R, we want to say what is R equivalent. And what I'm going to do here for a second is I'm going to take out this capacitor and say, well, wait, that capacitor, if I look in here, is seeing some kind of equivalent resistance there. Yeah, there's multiple resistors there, but there's some kind of equivalent resistance that that capacitor sees. And it turns out that this is an easy one. I did this on purpose. This is just 60K in parallel with 60K. Since they're the exact same value, that just divides by 2. So we get 30K, and then we have 30K plus 20K because they're in series, which gets me 50K. So my R equivalent in this case is simply just 50 kilo ohms. So that means my tau is 50 kilo ohms. And then I'll put my capacitor back in here, just 0.4 microfarads, times 0.4 microfarads. And if we do this computation here, we wind up with 20 milliseconds. And so an expression for the voltage, and it's the voltage across the capacitor, how is this capacitor discharging? This would be, well, my initial voltage was 200 volts, e to the minus t over 20, and on this case I'll write milliseconds, volts. And so that's my answer there. So there's not really a lot that's going on with this problem, but there is some work that had to be done. Of course, we first had to find the initial voltage just using some basic analysis techniques, and then we also had to find the equivalent resistance in order to find tau. Now, actually, I'm going to go ahead and continue with one of the last, well, it's actually the last objective in this course, because it's not going to take too long to cover, and since this video is only 7 minutes long, I'll go ahead and just tack it in here right now, and then we'll do some examples with this, or maybe just one example. So objectives here, we're going to look at what's called the forced response. And when I say forced response, what that means here is that we want to know, for instance, if I have, let's say, a circuit that looks something like this, how long for inductor to charge. So that's kind of what we're looking at here, is we're saying, okay, well, what would the forced response be? And we might have that inductor has some initial energy, it might have no energy, and so I want to have an expression for this. And now we could develop another set of differential equations and solve it like that, but again, I'm going to just give us the solution here. So for inductors, the forced response, or sometimes this is referred to as the step response instead of the forced response. Some textbooks call it the step response. They do mean the same thing. We get that the current is equal. Now, some textbooks don't like to write it this way, but I think this is the easiest way to understand it, especially when you look at a circuit, is I'm going to say IF, and that stands for the final value of the current, meaning the current after the circuit's been on for a long time, so the inductor behaves as a short again. What would the final current be through the inductor? Plus, well, we need to put in whatever the initial current is in the inductor. There might not be any initial current. That might be 0, so this might be 0. Minus the final value, or the forced response, e to the minus t over tau. So we still have the same time constant here. This tau is still L over R, so there's nothing different about the time constant. The only difference here is that we have a final value and also an initial value here going on as far as the response goes. And then for the capacitor, I'm not even going to bother drawing the circuit because you can probably imagine it's just replacing the inductor here. We have the voltage here. Whoops, I'm writing currents down here, and these should be voltages. E to the minus t over tau. And then, of course, remember for an RC circuit that tau is R times C. Now, these two equations here can always be used even for natural response. And I'm going to go back to an example we did in a previous video to illustrate how we could use it. Let's see here. Okay, right here. Let's look at this one here on how we could use that new equation and still get the same answer here. Well, I at t, we said, is I0 e to the minus t over tau. So let's instead use this I at t is equal to I final plus the initial current minus the final value e to the minus t over tau. Now, I0 and tau computations don't change. So how we've been computing the initial current and tau, there's nothing different about this. We were told it has some initial energy. We determined using that what the initial current would be, which was 4 amps. Using 2 kilo ohms and 120 millihenry, determined the time constant being 60 microseconds. Now the only thing that we'd have to do is what is I final? So we're saying, well, what's the final current through this circuit? And we should think to ourselves, well, there's no voltage source or current source, so eventually the current in this is going to be 0, just because this inductor is going to throw all of its energy onto this resistor, and we said it's going to dissipate it in the form of heat. So I final is simply just 0. And so if I do that with this equation here, then I at t is equal to I final, which is 0, plus the initial current, which is 4 minus 0, e to the minus t over 60 microseconds. And then, of course, getting rid of the zeros, because it doesn't make sense to keep the zeros there, we wind up with the exact same equation that we got when we did the example in the previous video. So that's what I kind of like about these step response equations, is we can actually use them for the natural responses as well. Sometimes that confuses some people, and if you don't like how I did that on that video, then just go back to the way that you were used to doing the problems. So the next video we're going to do an example of this, and then the final video we're going to look at is going to just kind of illustrate a few examples of how time constants are important in actual real applications. We already talked about it for like an inductor, like choking out a surge on a power line. But there are also other very useful applications of these time constants.